Here we have another example of an integrating factor which involves differential equation. So as we did from our previous video which involves integrating factor, we have to find the partial derivation of m with respect to y, which is equals to 2, and the partial derivation of n with respect to x, which is equals to negative 2. Negative 2. Sorry. Now, now that we've found out that this is not an exact differential equation, we can now solve for the integrating factor. So, partial derivation of m with respect to y minus the partial derivation of n with respect to x, which is equals to 0. Substitute the value 2 minus negative 2 is equals to 4. So 2 plus 2 is to 0. Now we can see a resemblance of the resulting value with the m factor. So we'll use the second case of our process in order to get the integrating factor. So 2 plus 2 is equals to 4 equals to 0, and we're going to use the second case, so 1 over m. We're going to substitute 1 over 2y multiplied to 4 equals to 0. So the resulting value will be 2 over y equals to 0. Now that we've got the value by subtracting the partial derivation of m from the partial derivation of n, we're going to get the integrating factor. So since we've established earlier that we're using the case number 2 of the integrating factor, so integrating factor is equals to case number 2, so negative integral of g of y dy. Substitute the value, so negative 2 integral of 2y dy, which will, so after integrating the exponent, which will result in to the negative of negative 2 ln y, to negative ln y, which can be simplified by changing the form of the exponent. So to ln y to negative 2 will result to the cancellation of into ln, and we'll get our integrating factor, which is y to the negative 2, or in simpler terms is 1 over y squared. 1 over y squared. Using our integrating factor, we're going to multiply it to our main equation, or the original equation, in order to get a new equation for our exact dE. So 1 over y squared multiplied to 2y dx plus 3y minus 2x dy equals to 0 will result to 2y over y squared dx plus 3y 2x dx dy over y squared equals to 0. Now we can solve this further, which can result to 2 over y dx plus 3 over y minus 2x over y squared dy. equals 0. So with this new equation that we get from multiplying the integrating factor to our main equation, we can now test it for exactness. So the partial derivation of m over with respect to y is equals to negative 2 over y squared, and the the partial derivation of n with respect to x is equals to negative 2 over y squared. So now we can observe that this is an exact equation. So we can just solve it as it is. So it is an exact equation. And now that this is an exact equation, we can now solve it as it is. So there is a similar partial function with the m function. So we can now integrate 2 over y dx by dx. So the integration of 2 over y dx is 2x over y plus the generic function, which is g of y. And now the integrated function of m will be used to be derived in terms of y. So 2x over y plus g of y will be derived and will become negative 2x over y squared plus g prime of y. Now using this equation, we can now cancel out like terms coming from the n function. So we'll use this equation and cancel out terms with the n function. So negative 2x over y squared plus g prime of y equals to the n function, which is 3 over y minus 2x over y squared, and negative 2x over y will be cancelled out since it has similar value. So g prime of y equals to 3 over y will be integrated. So g prime of y will become g of y and 3 over y will be integrated and will become 3 ln y plus the arbitrary constant, which is c. Now that we've got the value of g of y, which is equals to 3 ln y plus c, we can now substitute it to the integrated function of m. So 2x over y plus g of y equals to 0. So we substitute the value of the generic function. So 2x over y plus 3 ln y plus c equals to 0. And we can simplify this further by 2x y plus 3 ln y is equals to c. Now this is our final answer. Thanks for watching, guys. See you again for the next video.